Hi, I am Dr. Abhishek Joshi, and in this video lecture I am going to discuss about the fundamental operations of an optical receiver. So let's start. So in this lecture we are going to discuss about the basic things, that is the fundamental receiver operation, the digital signal transmission, the basic sections of an optical receiver and its operation. So whatever source we have discussed in our previous lectures, the receivers we have discussed in our previous lecture will be used, and we will be discussing the entire section, and all these basic section will be discussing that what is the purpose of each and every block. The source of noise in an optical receiver we are going to discuss, and the structures of an front end amplifier. So these are the topics which we are going to discuss in this lecture. So let's start with the fundamental receiver operation. So the design of an optical receiver is much more complicated than that of the optical transmitter, because the receiver must be able to detect weak, distorted signals and make decisions on what type of the data was sent based on the amplifier and reshaped version of the distorted signals. So as we know that the received optical signal, when it hits the optical detector, it may be PIN or avalanche photodiode. This signal which we are getting, the received signal, is very weak and it is distorted. Now this weak signal, when we are providing this signal to the detector, we are getting again the weak signal or weak electrical signal. So this signal is to be further amplified, then only we can detect our signal, and this signal is also distorted. So distorted and weak signals we are getting at the receiver. So we are having either the PIN or the avalanche photodiode. So to get an appreciation of the function of an optical receiver, we first examine what happens to a signal as it is sent through an optical fiber link. Since the traditionally fiber optic communication links are intensity modulated, so we know that the intensity variation is nothing but the intensity modulated, and direct detection. So directly we are detecting, also abbreviated as IMDD systems, that use a binary on-off keyed signal, that is also abbreviated as OK. So in OK is same as the amplitude shift keying. So let's discuss what is an amplitude shift keying. So for example, we are having a digital signal like 0, 1, 1, 0. So we can represent the signal in form of zeros and 1, or the signal will be 0, 1, 1 and 0. So this is our signal. This is the representation in NRZ format, not written to 0 format. So when we multiply, let's consider this carrier. Carrier will be your high frequency analog signal. So this is the carrier. This is carrier with respect to time, and this is our data, digital data. When we multiply these two signals, so when 0 will be multiplied by the carrier, we don't get any signal. So for 0, no signal. So this will be the output of on-off keying or ASK, on-off keying or ASK, amplitude shift keying. So if we multiply 0 by carrier, then we'll get nothing. So it will be simply 0. So this is the signal with respect to time. For the next data bit, it is 1. So 1 multiplied by any quantity will be the same quantity. So we'll be getting the carrier here. Then again we have 1. So again 1 means again we'll be getting the carrier. Then next bit is 0. So we don't get anything. So 0. So 0, 1, 1, 0. So this will be the on-off keying or amplitude shift keying version. So here we can see that either carrier is off for the bit or the data bit 0, and carrier will be on for the data bit 1. So the figure illustrates the figure in the next slide we are talking about. So this is the figure So we'll be discussing each and every section of this block and the operation of each and every block and what happens to our signal, that is the data which we are going to receive at the receiver side. So the figure illustrates the shape of the digital signal at different points along an optical link. So the transmitted signal is a two-level binary data stream consisting of either a 0 or 1 in a time slot of duration Tb. So this time slot is referred to as bit period. So one of the simplest techniques for sending binary data is amplitude shifted keying or on-off keying, that is OK, wherein a voltage level is switched between the two values which are usually on or off. So the resultant signal wave that thus consists of an optical pulse of the amplitude, that is V, relative to the 0 voltage level. When a binary 1 occurs, 0 voltage level is placed. When a binary 0 occurs, so depending on the coding scheme to be used, whether we are using an NRZ signal, whether we are using an RZ signal, it may be 1 or may not be the time slot that is having the bit duration, that is Tb. So bit duration simply means the single bit duration. For example, if data bit is 1, so from 0 to the duration when it having the transient. So for example here, so this is the 1 bit duration represented as Tb. So for simplicity, here we assume that when 1 is sent, a voltage pulse of duration Tb occurs. So whereas for 0, the voltage remains at its 0 level. So for NRZ, we are having simply 0, we have the 0 level. For 1, we are having the 1 level. So this is the representation of NRZ line coding. So in this figure, we can see that our bits are represented in NRZ format, not return to 0 format, where 0 is represented by 0 volt and 1 is represented by some non-zero quantity. It may be 1 volt, 2 volt or 5 volt, it may be any value. And the bit duration we can see here, it is bit duration is Tb, and when we are providing this electrical input pulses to our source of the optics, will be the LED or the laser transmitter. So LED and the laser transmitter is nothing but a transducer that converts the electrical input pulse to the optical pulses or optical signals. So we are having the data or the optical waves or optical pulses again in form of digital, but we are having some wavelength for the representation. Now this optical signals which we have generated either using the LED or using the laser is provided to the optical fiber. So we have already discussed in the very first lecture that there are different types of optical fibers. It may be a single mode fiber, it may be a multi-mode fiber. So depending on that, we are having the classification single mode, multi-mode or step index or graded index. So these are the different types of the optical fiber. So according to our requirement, we are using a specific type of the optical fiber. So now the optical signal is given to the optical fiber within the acceptance cone. So the optical signal travels. Now here we have the digital signal, but due to the different factors present in the optical fiber, it may be due to the impurities, due to the absorption or due to the presence of the noise, the signal will be distorted. So here we can see that our rectangular pulse are converted to or in the distorted form. So we are getting at the receiver side, we are getting the attenuated and the distorted optical power pulses. So power pulses, instead of getting the rectangular pulses, we are getting some Gaussian sort of the pulses. So we are getting these pulses. Now these pulses we have to provide it to the wind or the avalanche photodiode. So when we are providing these pulses, the distorted pulses to the PIN or the avalanche photodiode, these are the photodetectors which converts, again this is a transducer that converts the optical signal. So here what we have is, we have the optical signal. So now this optical signal will be converted again to the electrical signal, but this conversion will not remove any the distortion, because we have the rectangular pulses which we have transmitted, but at the receiver we are not getting any the rectangular pulses, we are getting some distorted form. So again we are getting some distorted pulse only, but here the form is changed. So here we have the optical signals having some wavelength, it is converted to the electrical signal, but no distortion is removed. We are having the same shape, so shape is not changed. As we can see here, the shape is not changed. Now this electrical current, that is pulse containing the photodetector noise. Now noise, we have some noise present in the signal, so noise is not removed yet. Now this signal which we have received is a very weak signal, so this is having a weak signal, and it is also a distorted signal, so it's very weak. So what we need is, we need a amplifier and a detector, so that our weak signal can be amplified, or the level will be increased or scaled. So due to this amplifier we are having the scaling. Okay, so now this signal is amplified and we are getting the higher voltage levels, and we need a filter to filter out the noise beyond the operating range. So we have removed, but we are getting the amplified version. So this is the amplified signal. So here we are getting the amplified signal and the amplified noise. Now here also the noise is not removed, so we have the noise in this signal. We don't have the electricals, the rectangular pulses. Okay, so electrical rectangular pulses we don't have. We have to get these rectangular pulses back to remove the distortion. So for that what we need is, so here again the signal is given to the next stage. Next stage is the decision circuit and the pulse regenerator. So decision we take if the value is above the threshold. For example, let's consider this pulse. If this pulse, let's consider this. Now let's consider the threshold at 0. Okay, and now if we check, if value is greater than 0, then we will detect it as 1. If the value is less than 0, then we will detect it as 0. So accordingly 1 0 1 0 will take the decision. So this is the working of the decision circuit, and the pulse regenerator will generate for the exact time pulses. So for example, here we have 1 0 1, but the shape is not proper, but after this decision circuit and the pulse regenerator, what we are getting is, that is 1 0 1 and the pulse is regenerated for the exact time duration. We are getting the pulse with a rectangular shape instead of the distorted pulse. So here we have 1 0 and 1. So this is the regenerated output voltage pulses. We can see now whatever signal we have transmitted in form of the electrical pulses or the optical pulses. Here we have the electrical pulses, here we have the optical pulses. So same pulses we are getting, that is the electrical signal, and this is having the purest form and without any noise and without any distortion, because again we have regenerated this signal. Now the last part is the signal processing equipment. So now the signal processing equipment will be used as a decoder for decoding our information, and this arrow denotes the time slot centers. So the basic sections of an optical receiver. So what optical receiver we have seen in the previous slide, we are going to discuss it one by one. So first element is either a PIN or the avalanche photodiode, which produces an electric current that is proportional to the receiver power level. Since this electric current typically is very weak, and a front end amplifier boosts it to level that can be used by the following electronic components. So after the electric signal produced by the photodiode is amplified, because we have seen here we have used an amplifier after the photodetector, that is PIN or the photodiode, it passes through a low pass filter to reduce the noise that is outside of the signal bandwidth. So beyond the bandwidth we are rejecting this noise. So how we are rejecting? With the help of the low pass filter. So this filter thus defines the receiver bandwidth in addition to minimize the effect of inter-symbol interference or ISI. So the filter can reshape the pulse that have become distorted as they travel through the fiber, and this function is called equalization. So since it equalizes or cancels the pulse spreading effect. So in the final optical receiver module shown on the shift and in figure, a decision circuit samples the signal level at the midpoint of the each time slot and compares it with a certain reference voltage known as the threshold level. So if the received signal level is greater than the threshold level, then 1 is said have been received. So we have what we have received, that is 1. So if it is above the threshold level, for example, the threshold level we have 0, then value, if it is value is greater than 0, for example, our received bit, let's say our received bit is BR. If it is greater than 0, then what is detected? 1. If our received bit is less than 0, then what will be detected? That is 0. So same thing is discussed here. So the basic section of the optical receiver. So the figure shows the basic section of optical receiver where we have the photodetector. As we can see here, we have the photodetector. In this photodetector, it may be PIN diode or avalanche photodiode. So we have already discussed the structure and the working of the PIN and the avalanche photodiode in the previous lectures. So you can refer that lecture if you want to know more about the PIN and the avalanche photodiode working. So this photodiode is actually converting the optical signal from the fiber, and the output will be the electrical signal. That will be very weak. So this optical signal, when it hits the junction of the diode, the electrons and hole pairs are generated. They are attracted by the opposite polarities, and due to this there is a flow of charge, and flow of charge is current. So we are getting the electrical signal in form of current. Now this front end amplifier, the front end amplifier is amplifying the signal. So here we are getting very weak signal, and this is converted to or amplified. So here the signals will be amplified. So once the signal is amplified, this is given to the filter. So here we can see the filter. So filter and the equalizer block, where it is filtering and equalizing our bits. So due to this filter, the noise is removed, and we are getting the equal pulses or equisample pulses. Now this is given to the sampling circuit. Now sampling circuit will sample at a given time interval, and so for example, we are taking the sampling time as TB by 2, then at every TB by 2 we will be having the sampling. So this will be the done by the sampling circuit. Next is the decision circuit, or we can say we will compare the with the help of the threshold value. So we'll take the threshold, some threshold, and we'll compare it. So decision circuit will take the decision. Now at what timing we will take the sample will depend on the clock. So we have to recover the clock. So we need a clock recovery, and this timing information is given to the sampling circuit so that we can sample at a particular time interval and with some period. Now the output voltage. The output voltage will be our electrical signal, that is our bits, that is in form of zeros and one. Whatever information we have transmitted from the transmitter. So let's discuss. So if a voltage is below the threshold level, so 0 is assumed to be have received, and to accomplish the bit interpretation, the receiver must know where the bit boundaries are. So this is done with the assistance of periodic waveform called the clock. So we need a clock, so which has a periodicity equal to the bit interval, and thus this information is this function is called the clock recovery or timing recovery. So this is the block which we are talking about, clock recovery or the timing recovery. So let's discuss the various sources of noise in an optical receiver. So what we have is, we have the photon stream, or you can say the optical signal. from the fiber. So here, for example, here we have some fiber, whatever fiber we have used. So here we are getting the optical signal. Now this optical signal is provided to the photodetector having the gain that is given by M. For avalanche photodiode, we have this multiplication factor, that is M. Now we have the reverse, that is bias resistance. Bias resistance, here we can see the bias resistance, and this is provided to the amplifier. So the photo detection and the quantum noise, we are having the Poisson's fluctuations. So Poisson fluctuations is there. So this is the source of noise. This is the source of noise in the received signal. Now when this optical signal, it is given to the photodetector. So once it is given to the photodetector, we have the dark current. So dark current means without any signal, if we are getting some output signal or the current, it is known as a dark current, which is nothing but the source of the noise. When we have the statistical gain fluctuation, so for avalanche photodiode, we have this, the gain fluctuation. So this gain fluctuation is also considered as a noise or the source of noise. So we have the bias resistance. So bias resistance is again have the thermal noise. So this part is having the thermal noise. Last part is the amplifier. So amplifier also have the noise. So that is also shown in this block. That is a noise due to the amplifier. So let's discuss the structure of the front end amplifier. So whatever amplifier we are using to amplify the weak and the distorted electrical signals. So this weak and the electrical distorted optical signals we have to amplify. So the first part is the photodiode. So as we have earlier seen that the photodiode is used to convert the optical signal to the electrical signal. So this conversion from optical to the electrical signal is done, and due to this we are having the signal. Now we have to amplify this signal. So before that, what we have to do, we are having the load resistance and the capacitance. Now this load resistance and the capacitance will be working as a filter. So this is the part of the filter which performs the filtration process. Now this filtration process is done so that whatever bandwidth we have. So if we have the optical signal having some bandwidth, let's say it is from 0.1 to 1 gigahertz. Now beyond 1 gigahertz it will be rejected. So this is the working of the low pass filter, low LPF, low pass filter. Okay, so this low pass filter is passing the lower frequency and rejecting the higher frequency. Now this filtered signal, now here for example, here we have the distorted signal and the very weak signal. Now due to this we are getting some filtered. So due to this filtration we are instead of getting very distorted signal, we are getting signal like this. Now this signal is given to the amplifier. Now this amplifier is amplifying the noise and the signal, because here the noise is not removed yet. So here we get the amplified signal having some amplitude. So here we are getting the output voltage. So this is the example of using the generic structure of the high impedance amplifier. So if you are using the trans impedance amplifiers, amplification can be done in another form also, that is a trans impedance amplifier. So here in this what we need is we need a photodiode. Photodiode may be PIN or avalanche photodiode. Now this is converting the optical signal to the electrical signal. Now again we need a filter, that is a low pass filter. So low pass filter is covered with the help of the shunt capacitance. So it is forming the low pass filter with the help of the shunt capacitance, and we are having an amplifier. It may be a op-amp, operational amplifier, because here we are getting the electrical signal. So we can amplify the signal and output will be a amplified version of the signal in the time domain. So whatever weak signals we are getting here will be amplified by the amplifier. With those three basic sections we can see here. One section is the photodiode, another section is the low pass filter, and the third section will be the amplifier section. So amplifier section is used for the amplification, filter section is used to filter out the band. So in this lecture what we have discussed, so these basic topics we have discussed, that is the fundamental receiver operation, how we can receive our signal and how we can amplify, filter and detect the signal. So these three basic operations we have discussed in terms of the optics. Then if we are using a digital signals, that is the information in form of either zeros and one, so how these information are transmitted and received. So we have seen, so what technique we have used, that is intensity modulation direct detection. So it is also known as amplitude shift keying, that is ASK, or also known as on off keying, double OK. So these basic techniques for the IMDD we have discussed, and the basic sections of an operational optical receiver and its operation we have discussed, and the various sources of noise in an optical receiver we have discussed. It may be noise due to the amplifier, noise due to the resistance, or we can say the thermal noise. So these noise we have seen, and even the noise due to the dark current. So there are different noises we have discussed, and in the last part we have seen the structure of an front end amplifier. So here we are going to stop this lecture. Thank you.